So I'm going to be talking about spectroscopy of protoplanetary disks. First, I just want to tell you, so I'm from Vassar College and not everybody knows it, so I like to advertise. On the left, you can see Mariah Mitchell. She was our first faculty member, a very famous American astronomer. And we're also where Vera Rubin did her undergraduate work, and that's her on the other side of the screen looking through a Vassar telescope. So when I think about the motivation for doing infrared spectroscopy of disks, I really think about this question, which is how do we explain the diversity of planetary compositions? And there's a kind of simple story that we often tell about this, which goes like this. So it says, if you're close to the sun or to a star, it's hot and your volatiles remain in the gas phase. If they're in the gas phase, they're not easily incorporated into solid bodies. If you're far from the star, then it's cold. So your volatiles remain in the solid phase and they are incorporated into solid bodies. So you get this range of types of planets where your planets close to the star are rock rich and your planets far from the star are ice rich. And this is known as, that's a simple version of what's known as this condensation sequence. This is a little bit more complex version of that story and what it shows you. So for example, if you were to look at Mercury here and draw a line down from Mercury, then everything to the left of that line would be incorporated into that planet. So Mercury is very metal rich. If you go all the way over to Jupiter, you have available metals and all different kinds of rocks, and also you start to have ices available. So that's the basic idea, but why is this not the full story? What are we missing? Well, there's several issues with this story. One is that there are many, many different chemical reactions, and each of those has a corresponding reaction rate. And it turns out that not all chemical systems in planet-forming regions reach equilibrium. And the condensation sequence essentially assumes otherwise. Another thing that's related to this is that because not all of the chemical reactions are able to come to equilibrium, you do actually have some history of your past chemistry. So it does matter what materials you got from the ISM in your disk. And it also means that transport matters. So if you're able to mix materials from hot regions and cold regions, then you'll get different kinds of chemistry. And again, the condensation sequence assumes otherwise. And then finally, this is more like an observational issue, but planet-forming environments encompass a really wide range of properties, including temperature, density, radiation field. So even if you could do all of the chemical calculations, we don't really have all the inputs. And I would venture to say we'll never really have all of those inputs because we're just not going to be able to have the observations that can constrain all of those parameters. So if we want to predict the chemical reservoirs out of which planets form, we really can't compute those from theory alone. We can't just compute them from first principles. So we need to directly measure chemistry. So that's what I do. So I think you should have seen something like this in Gwendolyn's talk this morning. But this is the basic structure of a protoplanetary disk. So it's kind of a cross section through it. And the main thing to note is that there's sort of three primary layers in a disk. The central layer is very cold, and so your molecules freeze out. The upper layers are exposed to a lot of radiation, so they become atomic. And then you have an intermediate layer, which is warm and can maintain molecules. And so with IR spectroscopy, that's what we aim to probe so that we can actually see the chemistry. And I'm going to focus on gas spectroscopy. Gwendolyn this morning talked about dust. So it actually turns out that it's not a given that you can see that molecular layer. And so we got essentially really lucky with the conditions in disks being such that we can see that layer. And this became clear with the Spitzer InfraRed Spectrograph. So you can see on the left here what the data actually look like. On the top is a spectrum. On the bottom is a model. And one thing to note about this is everything that's not labeled there is a water emission line. Water creates a slew of emission lines in the infrared. And more interesting than just detecting these molecules, we saw that the detection fractions are quite high. So if you look on the other side of the slide, the detection fractions around low mass stars, all of these bars are for different molecules, and they hover a little bit below or sometimes a little bit above 50%. And the data seem to suggest that if we had higher signal to noise ratios, those numbers would go up. The story is different for high mass stars, which I won't have time to talk about here. So that was Spitzer IRS. Where are we going with JWST? We heard a little bit from Nancy already, but show you some slides that are specific to disks. So on the right, the corner upper right here, you can see a comparison of JWST-MIRI with Spitzer IRS in the range that Spitzer had its high resolution mode. And so you can see even there, JWST does a lot better. And the main thing it provides is higher spectral resolution, and that pops up your line to continuum ratios. And it also helps you separate different lines. So it allows for you to go deeper in terms of column density, but also helps you interpret the data. But where it's really incredible is below 9 microns, where Spitzer did not have a high resolution module. And so on the left, you can see the comparison of those data with JWST-MIRI, and the comparison is just incredible. So Spitzer IRS, it just gives us some wavy information, pretty much no molecular detections, and JWST-MIRI is going to completely change that. And on the bottom, you can see also that JWST, by providing us those shorter wavelengths, allows us to look at things like methane and methanol, which were just not observable with with Spitzer. So that's the space-based story, but ideally what we want is not just inventory of all the molecules, but also some information about where they are. And so we do want spatial information. You can sort of do that with a space spectrograph, but it's difficult. It's much better if you get direct spatial information. And just to give you a sense of why this is difficult, I like to show this figure. So if you look at sort of 14 microns, there's this one really nice, what you think of as an emission line. It's actually at least four lines, all of which have very different quantum numbers. So they're probing very different excitations. So it gets tricky to interpret these kinds of spectra. So what does high resolution get us? It actually allows us to use the Doppler shifts of the lines to determine where the gas is. So the basic idea is you resolve your line, you measure the Doppler shifts, and then you use Kepler's third law to tell you where the gas is. So this is an example in black as an emission line, and showing 3 different models, and the best fit has radii of 0.05 AU. You can also get really detailed spatial information using a technique called spectroastrometry. This also requires resolved spectra. And the basic idea is that you put down your slit. That's what my little blue box here is. So you put your slit on top of your disk. And then you ask not just what is the spectrum, but what is the spatial position of the emission as a function of wavelength. So if you ask, where is the blue light coming from? Well, it's coming from the left side of the slit. If you ask, where's the red light coming from? It's coming from the right side of the slit. And you can plot that position versus wavelength. So that's what's shown here on the right. On the top is just a regular emission line, but just below it is the spatial position versus wavelength. And that can give you very precise information. And of course, it depends on position angle. So if you move your slit around, it'll move the shape of that curve. And so there are 3 position angles shown here. So high resolution spectrographs have been really essential for providing us spatial and kinematic information about the molecules. And here are some of the key players in that field. So in the near infrared, it's been really Keck NIRSpec and VLT CryoRes. And then in the thermal infrared, some of the key players have been VLT VZIR, the Texas instrument, which has been available on Gemini as a visitor instrument, and also Gemini Michelle. So that's a general story about spectroscopy, but I'd like to tell you some more specific stories so you can see how the space and the ground observations play together and how they complement each other. So the first story I'm going to tell you is about transition disks. It's kind of a misnomer. You should think of them as really protoplanetary disks that have a gap in them. And so that's what's shown here on the left. It's a disk and it has a kind of gap in the middle. And this is a particular disk where there's been some evidence for like a point source in the middle that might be a planet, but I think it's still under debate. But we still think that these gaps are likely formed by planets. And that picture that I showed you in the last slide, that's a picture of the dust. So these gaps are really in the dust. And we learned very early on from infrared spectroscopy that these gaps are not completely clear. They do actually contain gas. And we figured that out by looking at CO emission lines and looking at their Doppler shifts and figuring out using Kepler's law to figure out where the gas is. And I just like to mention, for some reason, ALMA observers, they love to say, we discovered gas in the gaps of transition disks. And this was done by infrared astronomers many, many years ago before ALMA came to be. So don't listen to them. So we detected gas in these disks, and then we can also ask, what is the chemistry of that gas? And is it any different from disks that don't show this evidence for planetary or planets opening gaps? And the answer seems to be yes. So this is a little bit hard to read this slide if you're not an expert in looking at these spectra, but on the bottom, you can see what a typical spectrum looks like. It has exactly the bumps and wiggles that you would expect from water vapor. And then all of these spectra on the top, they also have bumps and wiggles, but as far as we know, these are mostly noise, so they do not show the characteristics of water vapor. And those are all disks that have gaps in them. So it seems like the gaps matter. There was, however, one really interesting disk that was kind of in between, where it has a gap, but it also shows some water vapor. And this one's a little bit different than those other gap disks because it has kind of an inner ring of dust. This is an artist's rendition of what that might be. So you can see kind of like an inner region where there's some thick dust and then a gap and then your outer disk. So that was some space-based information, but we didn't really know where the gas was. So we can do that with ground-based data. And this is a beautiful spectrum from the TEXI spectrograph. And I'm not sure if this looks beautiful to non-ground-based astronomers, but I think it's incredible. So all three vertical lines here show water vapor emission lines. And then we can use our tricks of the Doppler shifts plus Kepler's third law to figure out where it is. So here's a model of, actually this just shows the data here in black, and then we can measure where the Doppler shifts come from. And so we think it's consistent with the water kind of coming from right outside of this inner ring, and certainly it's within the gap. So what is this telling us about chemistry? Well, it seems like there's a very sensitive switch to the chemistry in these disks with gaps. So water, it turns out, is produced all the time via chemical reactions, and it's also destroyed constantly via ultraviolet radiation. So there's kind of a balance between those two. And for some reason, we can have a very sensitive switch that tips us in the direction of having water or not having water in these disks. And understanding exactly what the chemistry will be seems to depend very sensitively on the structure of the disk. So that's story one. Story two is about C to O ratios and what they might tell us about disk transport. So to understand this story, first you have to realize that if you have freeze out of water, you end up with oxygen-rich grains, and then your surrounding gas is carbon-rich. And so you can measure this C to O ratio of the gas with molecular tracers, and two particular tracers are HCN and H2O. So that gives you your carbon here in the HCN and your oxygen in the H2O. Now what we actually measure with spectroscopy is the inner disk region. And so that inner disk C to O depends on how efficiently the gas and the grains are transported to the inner disk. So we think there might be different stages of that transport. So early on in planet formation, you have efficient transport of both grains and gas to the inner disk. So even though you preferentially have this carbon-rich gas and oxygen-rich grains, if you move them both to the inner disk at the same time, then your overall C/O ratio in the inner disk remains the same. We think there's a later stage where grains grow to such a size that they move very rapidly inwards relative to the gas. So that will move your oxygen inwards, increase your oxygen in the inner disk, and then decrease your C/O ratio. And then there's a final stage where perhaps the planets have grown so large that they start to block the grains from going in. And in that case, you deplete your inner disk of oxygen and you then increase your C/O ratio. And what's neat is that we actually saw a range of C/O ratios as traced by HCN and water in protoplanetary disks. So that's what I'm showing here. You can see these ratios. And so this high C/O ratio, we believe that's the case where water transport is being blocked. So you kind of block your oxygen from going inwards. And then this other corner is where you have efficient transport of water. So you increase your oxygen. And then if we ask, what do those C/O ratios correlate with? They actually correlate with the disk mass. So here are some high disk masses. Those seem to have the water transport blocked. And one reason for this could be that the higher mass disks are more likely to form planets more quickly. And if they form the planets, then they start to block the transport of the oxygen inwards. Okay, but that's a space-based result. And so we didn't really have location information for these molecules. And one of our worries was we're measuring HCN water line flux ratios. We're not really measuring C/O. So could it be that, for example, the HCN and water are just being emitted from different parts of the disk and they're representing differences in temperature or differences in emitting area or something like that? So we went to the ground, and these are some beautiful spectra from TEXES showing HCN and water. And what we can see here, actually on the bottom, if you look at the HCN, the little blue on top of the HCN line is the water line rescaled. And essentially they have indistinguishable line shapes. So we do think that they're emitted from the same region and that this HCN-H2O line ratio is a proxy for the C/O ratio. So that was pretty exciting. And there's been a really neat update. This is work by Andrea Bonzatti that he's just published, showing that this C/O ratio also seems to correspond with ALMA dust structures. So let me just explain this plot. He actually has reversed the axes here. So now we have water to HCN ratio, so sort of an O to C ratio. And in this corner, in the left corner of the plot, is where you have efficient water transport. And in the right corner, you have your transport blocked. And if you look at the disks that have efficient water transport, they actually look very small in ALMA data. So what that suggests is that we're actually seeing the transfer of grains. So the grains have actually moved in and made this really small disk. And in the disks where we think water transport is blocked, we actually see that the disks are large. So it seems like the grains have not moved inwards. So this is really cool result where we use infrared spectroscopy to tell us about transport. And then we're actually seeing that later reflected in dust data, which is also telling us about the transport. So this is a really cool result. Now there's going to be some new data coming out soon over the next couple years or so from VLT-Vizier. So I just wanted to advertise that. So this is some data that I've been working on. On the bottom, you can see all the blue vertical lines. Those show you water vapor emission from a disk. But on the top, we actually have spectroastrometric data. So that would be telling us the position as a function of wavelength. This particular data set, we do not see a signal, but that's actually also exciting because it gives us some upper limits on where the gas is. So it kind of constrains the gas to certain distances from the star. And this program that we've been working on, this is led by Klaus Pontoppidan, is really exciting because it combines water, OH, and neon-2 plus this spectroastrometry. And neon-2 is a disk wind tracer, so it allows us to see if there's any connections between chemistry and disk evolution. Now, this science to me is very, very exciting, but it has been really challenging, especially from the ground. And the reason is just that the line to continuum ratios are very small. So doing this with even the cutting edge telescopes today, the 10-meter class telescopes, is really difficult. And that's going to change if we can do molecular spectroscopy with extremely large telescopes. What's going to happen is that we'll be able to detect these molecules. We know they're there from space-based observatories, but if we can see them from the ground, we can do this really detailed work, and we'll be able to do it really for probably the great majority, if not almost all, protoplanetary disks in nearby clusters. And once you start talking about 30-meter telescopes, you actually have enough spatial resolution that you can just directly see where the molecules are on the sort of sub-AU scales. So you can start to make chemical maps even without using these tricks, but these tricks are still available looking at the Doppler shifts and spectroastrometry, still available, and you can get really detailed chemical information. So I think this field, in a sense, is still young, and I really look forward to being able to do this with the 30-meter telescopes. So that's it. Thank you.
Thank you, Colette, and thank you for staying well on time.
Sure.
We have a question on Slack from Jana Martins-Franco, who is asking, do you think PHs could be an interesting science case for MIRI?
Yeah, I mean, that's a good question. I think you should definitely check with Gwen Mias because she would probably be the expert on that. You know, they were detectable with Spitzer IRS, and there were some interesting stories. I think that they're detected, for example, more often in Herbigs than they are in T-Tauri stars. I don't know if I don't know for sure if we get a lot more information from MIRI as compared to Spitzer, because that spectral resolution doesn't get you as much for the solid state or these sort of intermediate. I don't know if pHs are considered solid or gas, or sort of in between. But you don't get a ton more information from MIRI with the higher spectral resolution because your features are so broad. But you should definitely check with Gwendolyn. I'm sure she has more to say about that.
All right, thank you. Another question from Roy van Boekel. It's on the oxygen over carbon versus disk size plot. Compact wet continuous disk on the left with large dry ring disk on the right. Is there a correlation between disk size and disk mass and therefore planet forming potential?
Yeah, so I think this is still something that's being debated. So if you look at this plot here, on our x-axis, we have disk mass, but that's really disk flux. It's really millimeter flux interpreted as a mass, and that assumes that you have optically thin disks. And then there's now been some results that are showing that the millimeter flux is correlated with the size of the disk. And so as I understand it, there's still kind of some debate about what is the optical depth in the millimeter wavelengths for these disks. And so if you measure a flux, are you measuring just the size of the disk, or are you measuring its mass? So I think it's still not entirely clear. I know there have been some papers suggesting one versus the other. So I think we'll just have to wait and see whether this is really about so is our plot about disk mass for real, and we're really learning about planet forming potential, or are we just tracing the size of the disk with two different parameters?
Okay, there is a follow-up question from Emilia Bayo. The question is, are all of those single objects and similar mass central objects?
Oh, okay, yeah, let me think. I don't 100% remember if all of these are, so let me think. I think D sharp has a couple of binaries in it. These are all I think these are mostly D sharp images here. There are a couple binaries, but I don't think it would be enough to have a big influence because I think there's only one or two. And then what was the other question? Oh, about what their masses are. So they do have a range of masses. I think Andrea looked into whether there are any trends with mass and there was nothing obvious. Yeah, that, and D sharp, does it include, I think it does include some Herbigs as well. So it's sort of the full range of masses here.
All right, we'll do one more question from Slack. Nicholas Coelho has a question. Do you expect any differences in terms of HEN over H2O between disks in binaries and single stellar systems?
I really have no idea what to expect there. I mean, I think we don't have really any results about chemistry and how it differs in binaries versus singles. We obviously have these very large differences in the amount of disk material that we find and that the distances that we find that material at, but I don't think we've ever talked about, let's say, two disks, one of which is single, one of which is binary, and they have the same distribution of mass, but end up with very different chemistry. I don't think we've ever had the statistics to ask those kind of questions, but that's a really interesting one.
Okay, and I also have one last question. So you didn't mention anything about isotopologues, which, for example, you do see quite a bit in disks with an instrument like ALMA. Do you think that's mainly a matter of sensitivity? And if so, what do you expect from the next generation of instruments in this regard?
Yeah, that's another good question. So we think that JWST-MIRI is right at the border of potentially being able to measure some isotopologues. There have been some CO isotopologues that have been measured for disks in the near infrared, but for mid infrared, I mean, obviously we would love to see something like H218O or HDO. So we're right at the border. The problem with the challenge for something like JWST-MIRI is always the fringing, which limits your signal to noise ratio. So I think if we can really get a handle on the fringing, then we can start to integrate for long enough that we can detect these less common features.